So this is Maple to do a bunch of different kinds of integration. We've already done differentiation in a different video. This is the one, if you do a search on the internet, you will find this Romberg integration Maple worksheet. Gives you the explanation of what all the parameters are. And then in essence, they've written a program. Right. If you're going to write a program, you might as well just write a program as opposed to going into something like Maple and writing a program inside Maple to do something that it's going to be doing anyway. It does turn out to be a little bit easier than a spreadsheet. Right? So if you've got Maple, you could get this to work. There's also a free Maple player out there that you can get from the MapleSoft website. It should be able to run most of this. But I really don't recommend it. If you're going to do Maple, just go ahead and get Maple. Then, of course, here it's doing e to the minus x squared over 2. It's that 1/2 x squared. And it's going to evaluate this thing and try and give you the results. I would prefer, and Maple would probably prefer, and it's faster to use the built-in procedures that are already in Maple rather than reinvent the wheel. So what you do is it's with student numerical analysis, and you put in this colon simply because if you don't, it will spit out huge amounts of information as to all the packages it's loading. The first thing that I've done is a Romberg integration. As the function I've chosen is just the square root of 1 plus sine x, which would be a bear and a half to integrate by hand. I give it the a and the b. Right? I want to go from 0 to 8. Right? So that's a fairly robust interval over which I want to integrate this thing. And so to do a Romberg integration over this, there's a built-in quadrature command. Right? You give it the function, you give it the range, x is equal to a to b, and you tell it what method you're using. Notice this thing is saying method equals Romberg, and you have to tell it the interval, which is 4. I chose 4. And then I want an output of a value, right? And it spits out the number for me. If you want to see what it's doing and how it's churning through the approximations, simply change the output method to plot. Notice that it's doing this is its first approximation, which is terrible. Right, this is the second one. It's doing sort of a midpoint, and it's got 2 trapezoids, because remember, Romberg is based on trapezoidal. Right, and then 3, it's got this one, it's got that one, it's got that one, and it goes to the final. And now when you get to the last one, it's chopping it up fairly fine. But it's still overshooting here by a lot. Actually, if you're looking for high precision, you would go to a much larger value than Romberg 4. You would go to Romberg like 16, and that would clean all this up tremendously. The last part is if you actually want to see what it's doing and how it's doing it. You ask for output equals information. Right? It won't give you the graphs, but what it will do is it'll tell you this is the thing I'm trying to integrate. That's the interval I'm trying to integrate it over. Right? This is the value I get. This is how I got the value. Right? 4 applications of trapezoidal rule. Right? This is the approximate value. This is my absolute error, 0.05. Right? So you're anything more than 2 decimal place accuracy, not so much. Right? Relative error turns out to be 0.72%. Right? That's pretty good. Right? And here it's giving you exactly what it did in the spreadsheet. It's giving you the first pass. It's giving you the Richardson extrapolation of that first pass, the Richardson extrapolation of the extrapolation, and then the final extrapolation, and that's how it gets the reasonable answer. And it's doing 9 function evaluations to get there, right? So you know exactly how much computer time this thing is using to sort of churn through it all. Again, just if you hit the 3 exclamation point buttons in here, it will recompute the entire spreadsheet or worksheet in Maple, which it needs to do because it needs to load this numerical analysis right before it can do anything else. And then you could go ahead and go back in here and you could change this to 8. And then I would change that to 16 in each of these steps to see what it's doing and how it's doing it. Maple does work very, very quickly, though. I highly recommend it, which is why if you go on to an engineering school someplace, they're going to give you something like Maple or MATLAB or Mathematica. If you go to NJIT, it's MATLAB. But if you know one of these, you know them all. Really, because they're all basically the same. Under adaptive quadrature, so this is the other technique that you can use. Instead of Romberg, you do adaptive quadrature or then Gaussian quadrature. Again, here I changed it to the square root of 1 plus cosine x just for giggles, but I used the same interval, 0 to 8. Here, it's method Simpson, 4 partitions, and the output value, right, because the numerically approximate this thing. And notice, instead of quadrature, this function is called adaptive quadrature. It's doing exactly what it says it's doing. Right. And so it's spitting out that output value. Again, if you change it to plot, it's telling you, okay, I've picked all these individual little dots as my intervals and subintervals, and it's drawing those lines, and that's how it's doing the Simpson integration that it's adding all together. Notice there's not a whole lot of overshoot here, and it's pretty good, right, for getting the results. And it's telling you a bunch of information here, integral value and approximation. Right, it's good to 3 decimal place accuracy. Right, so if it can't do the actual integral, it'll tell you. It'll just leave that piece out. But the approximation is this much. It's good to 3 decimal place accuracy. So you go out to here if you ask it for output of information. Be ready for a lot of information, depending upon how big your interval is and how big the partition is. Here I've asked for adaptive quadrature, and I've changed it to method trapezoid from method Simpson. You could leave it as Simpson, but I chose to use the trapezoid rule for this particular one for adaptive quadrature instead. What it does is it's given me 7.974. This one, so they match Simpson, and this one matches up to 4 decimal places. All right. But notice what it's doing. It gives you each individual interval. It tells you the status of that interval. Was it successful or did it fail? Can I use it? Can I not? And if it is, that's my iteration history. That's all of the values that it's churning out and the interval it's using to churn out those intervals. And it gives you every single interval all the way up to, now you know why I have the tabs closed. All the way up to the very end. Notice it's 485 functions that it evaluates to be able to get from the left-hand endpoint to the right-hand endpoint of this 0 to 8. I did adaptive quadrature. Again, I told it adaptive was true. I asked it for the Newton-Cotes method, and here I can specify an error. I want this thing good to 10 to the minus 4. And again, you output the information. Right? You can tell it Newton-Cotes, and you could tell it 10 to the minus 6. And again, it went through and did all of the points, trying to compute out to, it's still needed 485 iterations to be able to get me that 4 decimal place accuracy, right, that I asked for right here. Right, now, 4 decimal place accuracy was exactly what I had before anyway. All right, so if you just change this value, change this to 10 to the minus 6, and you hit enter, it should recompute the whole thing, right, and it will give you 10 to the minus 6 accuracy. But be prepared to sit there for a long time. I'm working on a fairly new Mac, and I've got 16 gig of RAM in mine, and churning out these took me 2.5 minutes. I hit enter and it just spun its wheels for 2.5 minutes before it started spitting things out. So if you're working on a slower machine, I won't say Windows, but that too, be prepared to wait for a very long time. The nice part about Maple is that it will run on a Mac. It will run in Linux, not surprisingly. And then it will also run on a Windows machine. For the Gaussian quadrature, I went back to the square root of 1 plus sine x, right, just because. Notice I go back to my quadrature rule, right, and I tell it Gaussian, and I have to give it intervals. Notice I did both a Gaussian 4 and a Gaussian 8. And if you take a look at this, this one is 7.864. This one is 7.8626. All right, so someplace in that third decimal place, I am getting a difference in the data and in the precision of the output. If I change this to a 16, I will get even more accuracy. And of course, if I change the output to plot, here I just did Gaussian 4 and I put out the plot. Notice it tells you the points that it's using to evaluate the thing. It doesn't give you the subintervals anymore. The integral is actually 8631. All right, so this one overshot, Gaussian 8 undershot by just a little. But this one is definitely closer because if I rounded it up to 3 decimal places, this one's going to give me 863 because this is 8626, right? Whereas this one is just 8640, right? So this one's over. This one, if I round to 3 decimal places, I get the correct answer. So if I come down here, and again, I changed it to output information. Notice for Gaussian 4, where I'm getting the integral value, and then the approximate value is the 8640. It's telling me it's doing 40 iterations or evaluations. For an 8, I am going out to 80 iterations, so it's doubling the number of iterations. Right? So it is going to take a fair amount of time to do this. If you do this and you go out to, say, 32, right, this number explodes, and your computer will sit there and chug a little bit, depending on how much RAM you have and what your processor speed is. Your computer is going to chug. Depending on your processor, the other thing is, if you remember, the very, very first thing we did was numerical round-off and numerical error. Depending upon your processor and sometimes your operating system, even if you take this thing and go out to 32, it will not give you an appreciable improvement at all. But notice the absolute error is in the 1, 2, 3, 4th decimal place here. That's good. And relative error, relative percent error is 0.006%. All right, so that's really very good in my world. And I think, that anybody should be, fairly happy with that. So that is using the built-in functions. I give you both. I give you this Romberg integration thing where it's got the programming in it. But I also give you this. So if you have Maple and you want to go ahead and use the built-in functions to do Romberg, adaptive, and Gaussian, please feel free to do so. And you can go ahead and just change the name up here so it's not my name. And it's your name, and you can submit those as the basis for your both your homework problems and some of your project problems. Again, you should be comparing these. You should compare Romberg to adaptive to Gaussian for the appropriate cases. The last video that I'm going to do in this particular section is for programs, and I program in C or C++. Not Java, unfortunately, but I do include a link to a Java program, which hopefully will help you. But I'm going to show you some C++ programs.